That again. Good afternoon, everybody. My name's Tim Green. I'm a co-director of the Energy Futures Lab. I'd like to welcome you to our event today, in which we launch our briefing paper examining the impacts of COVID-19 on the energy system, combining supply and demand side perspectives from some research groups across Imperial College. For those of you joining us for the first time, I'll just give a short introduction. Energy Futures Lab is one of 7 global institutes at Imperial College London. It was established in 2005 to address the world's major energy challenges by bringing together teams of researchers with a variety of backgrounds to carry out multidisciplinary and high-impact research. In a moment, we'll hear a joint presentation from several of the co-authors of this briefing paper, but first, a few pieces of necessary housekeeping. The event will last 1.5 hours, and you should be able to see on your screens now an agenda. You will see that the presentation will last about 25 minutes, and it will be a short overview of each of the chapters of the report. This will be followed by some remarks by our invited panelists, and we will then move to a question and answer session. That will last around about 35 minutes and involve the panelists and the presenters. There'll be an opportunity to submit questions via the Q&A feature in Teams as the event progresses, and I'd encourage you to do that, and also encourage you to read the questions and vote them up and like them. That will help us decide how to prioritize the questions, because unfortunately we're only going to be able to get to a few of those questions during the course of the event. The event is being recorded and it will be made available on our YouTube channel. I would encourage you to share that with colleagues who weren't able to join us today. The briefing paper itself is available for download from the Energy Futures website now, but we'll also send a link to you after the event to make it a little bit easier for you to get to the right place of the website. So with all of that said, let me now kick off the presentations of this briefing paper by handing you over to Amy Trask.
Hello, thank you very much, Tim. I don't think I'm on mute, but if I am, please correct me. So thank you very much, everyone, for attending the launch of this event, the impact of COVID-19 on the energy system. I'll be presenting today alongside a few of my co-authors, namely Dr. Mirabelle Muûls, Dr. Aruna Sivakumar, and also Dr. Luis Badesa. So without further ado, let's get into it. The outbreak of the COVID-19 virus in 2020 it wasn't just a health crisis, it also caused massive economic and social disruption. The effects have been widespread, with also a significant effect on our energy system. Partial or total lockdowns imposed by governments to mitigate the spread of the virus meant we saw an increase in the time we spent at home and less time traveling. This altered our daily activities, routines, and resultant energy consumption. The paper presented today explores the extent to which COVID-19 impacted the UK's energy sector over the course of the first government-mandated lockdown. It's based on research from several aspects of the integrated development low-carbon energy systems, and I'll challenge anyone to say that 5 times fast, at Imperial College London. It's a collaboration of working groups from a very diverse background and hopefully provides a narrative that reflects the multidisciplinary impact that COVID has had on our energy system and extrapolate the lessons learned in terms of working from home policies, electric vehicles, and managing low carbon grids. So in this presentation, we'll first look at the national scale impact on electricity consumption and the policy influences that may have played a role in lowering demand. We'll then take a closer look at how this impacted our day-to-day lives in terms of household consumption. Findings from an activity-based model apply to assess how 2 main drivers of future energy consumption, namely working from home and electric vehicles, could impact household demand in the future, are then presented. And finally, we'll look at the operational challenges faced by the electricity systems operators in Great Britain to maintain stability during a period of high renewable and output and low demand. And then we'll round off with some of the main conclusions of the report. So first of all, the changes in electricity use at a national scale and the policy influences that could have affected it. So the collective closure of offices, buildings and industry meant that national demand decreased overall from mid-March. As a result of lockdown, weekday demand fell by 13% in the first quarter of the year. This was a downward trend that continued throughout April 2020, where at its lowest, demand was approximately 19% lower compared to prior years. You can see here in the graph that the demand levels are comparable to the 1980s, and during this time we were actually just recovering from a recession, and there are also 10 million fewer people in the population. So during the time period in COVID, favourable weather for solar generation, reduced demand, and also low generation costs meant there was a higher utilisation than for renewable energy resources than average. So we reached a plethora of milestones in regards to electricity output. In April, we set the record high for the output of solar power. May became the first month in Great Britain's history in which no coal was used for electricity generation. And on average, 46% of electricity came from low carbon sources in June. The high share of renewables in the grid and low demand also had consequential effects on power pricing and carbon emissions. So in terms of power pricing, the reduced need for fossil fuel generation during lockdown, combined with falling international gas prices at the time, pushed electricity prices down, and they're actually the lowest that they've ever been in 2 decades, almost 2 decades. With regards to carbon intensity of the grid, with so many renewables on and such low demand, the carbon intensity actually declined. And over the course of the first and second national lockdowns, there was a 22% lower carbon emission output as a result of the grid than the previous 3 years. So it's interesting to examine how specific policies under lockdown played a role in suppressing this demand, as this allows us to assess their long-term applicability in lowering national electricity consumption. So data analysed in the briefing paper determined that out of all of the containment and closure policies implemented under lockdown, workplace closure was by far the most notable in terms of reducing demand. Required closing for all but essential workplaces correlated with an 18 to 20% decrease in electricity demand on a national level. Whilst the closure of workplaces has several consequences for business and their employees, for example, we're all familiar with the furlough scheme and the rise in redundancies, particularly in the hospitality sector, there's quite a lot to consider when we come to workplace closure. However, remote working is really the only option that has potential to be long-term implemented. So the rise in teleworking and impact it had on household consumption is therefore something warranting further investigation. And I'll now pass you on to Dr. Mirabelle Muûls to discuss the impact it had on a household level during COVID.
Hello, everyone. My name is Mirabelle. I'm an assistant professor in Imperial College's Business School and work in the field of economics. So the work I'm going to show you today is the first part of a joint effort across the Business School, the Grantham Institute, and the Urban Systems Lab. So the part I will present is work we did with my PhD student, who's now graduated, Quentin Coutelier, Ralph Martin, Jeffrey, and others. So what we were keen to understand is, although, as Amy said, the overall national consumption of electricity decreased, we were keen to understand what was happening in the households, and in particular, what we could learn from that episode of very unusual lockdown and everyone being at home, to understand what we could learn from it for future low carbon. So to do that, we were very lucky to partner with Octopus Energy, who've been at the forefront of developing and using data on consumption behavior. And we did this in 2 ways. So the first was David Morales, a student working with us, collected data through a survey to understand how households were changing the way they consume electricity, and in particular in terms of teleworking. And so we were lucky to survey more than several hundred households and to cover about 1,000 teleworkers or workers in our survey. And as you can see here, there was a great variety in how many days people worked from home and how many days they commuted. But overall, outside lockdown, they worked less from home and commuted more than during lockdown. And on the next screen, what you can see is that it's not a homogeneous thing, that obviously, key workers kept traveling. On the right side, you see that 12% were not teleworking, but there was clearly an increase in the number of people working from home, and our survey covered those types of households. The second type of data that we used was Octopus's smart meter data. So the households we surveyed were households that had been customers at Octopus for more than a year before lockdown, and who had smart meters, so we could measure how much they were consuming at different times of the day, on different days of the week, etc. And so, as you can see on this graph, what we measured was their consumption on average per week, every week from a year before lockdown to July 2020. And until there started to be an effect already a bit before the national lockdown, but overall through lockdown, consumption increased. So what we tried to do is to, of course, control for what different households are. So this increase that you see on this graph is controlling for the weather and the temperature. It's controlling for any given household. And on average, what we find is that they increased during lockdown their electricity consumption by 10%. But if you're thinking of a low carbon world, what matters is not really how much they consume, but also when they consume, and where at the point of consumption, how low carbon the grid's electricity is at that given hour. And so what we did is we looked at the pattern of electricity consumption throughout the day, and in blue you can see the pattern outside of lockdown, so mainly in 2019, and what you see that is the usual pattern of a peak in the morning when everyone wakes up, and then a peak in the evening when everyone gets back home. And the average being the average consumption by the household. In orange, you see what happened during lockdown. So as I told you, a 10% higher consumption on average. But what's interesting to see is that we also have a different distribution throughout the day. So if we bring the two averages to the same level on the next slide, we can see that the pattern is different in that in the morning, the households would start the day a tiny bit later. They would consume more during the day, and the evening peak was slightly lower, but also earlier in the day. So this is where our main learning happens, is that despite a huge shock where everyone is at home, there is a pattern, a change in the distribution and in the pattern, but is it significant enough to really decrease the carbon content of a household's electricity consumption? So to do that, on the next slide, we tried to understand what this 10% electricity increase meant in terms of carbon content of that usage. So first, you would expect that the different hourly pattern would have moved some electricity consumption to earlier in the day where there are more renewables in the system. But at the same time, if we click, the grid was less carbon intensive. So when we take those two elements together, we find that actually this 10.4 increase in electricity consumption actually resulted in a 6.7 decrease in the carbon content of that electricity. So that seems really promising, and you would say, okay, great, teleworking moves demand through the day and we became carbon negative. However, we want to isolate the change in the pattern of consumption from the carbon intensity of the grid. And when we therefore take the carbon intensity pre-COVID in 2019 and apply it to the new electricity profile, we find that actually the carbon content increased by 7%. What's promising is that this 10% increase in electricity did not lead to a 10% increase in carbon, but it's not sufficient for a complete neutrality. So what the main message is saying, demand can go away in leading us to a low carbon futures. However, it also has to come from supply and from the system. So next, Aruna is going to tell us about how we can try to understand more generally how electricity consumption changes.
Thank you, Mirabelle. Hopefully you can all hear me. I'm a reader. My name is Aruna Sivakumar, and I'm a reader in the Center for Transport Studies at Imperial. And the work that I'm presenting here is work with my research team, research fellow and postdocs within the Urban Systems Lab. And of course, it's built on other PhD student research and so on, not all of whom are on the actual writing of this book. So I must acknowledge all of that. Exactly as Mirabelle just said, we can use descriptive analysis of changes in energy consumption due to the lockdown conditions to understand behavior, to draw implications from all of that. But from a planning perspective, we need a tool and we need the ability to analyze a variety of future scenarios. We don't actually want to live all those scenarios. We want to know what would happen if we had a variety of future scenarios. And we want a model that can realistically tell us what would happen. And so what we've been focusing on in my research group is to develop an agent-based model that can help us analyze a variety of policy scenarios. And the reasons, the motivations for this was way before COVID. So this is development that we started many years ago. And the reason for this is that it was always clear that work from home and virtual activities in some form will be a prevalent modality going into the future. The question is not whether, but it's about how much, what, and when. And it was also clear that electrification of transport is going ahead in some form or the other, thanks to the ban on new and petrol diesel cars to a good degree, but also more recently we've observed exacerbated by the fuel crisis as well. In parallel, there's been a focus on drawing upon flexibility in demand through a variety of different demand side response policies to balance the grid. And in some sense, all of these work together to impact the patterns of demand that we're expecting into the future. And so it was clearly important to develop the capability to model scenarios that can consider all these factors jointly and at a high spatiotemporal resolution. And that is basically the results of such a model is what I'll be presenting in the next few slides. On the next slide, this is fundamentally the modeling methodology we use. We use agent-based microsimulation. In other words, we're simulating all the agents in a synthetic population for the study area, but the simulation is not based on ad hoc rules or decision trees. It's based on microeconometric models of the behavior of these agents that is calibrated on real data from the census, from the UK time use survey, from a data set called the META data set, which we derived from Oxford University and so on. So all of these come together to calibrate a set of models, which are then implemented in an agent-based simulation platform. And this is drawn, this simulation is drawn based on 4,200 households over the study area using the UK time use survey data. And the activity patterns of these individuals are simulated using observed time use diary data that tells us when people are performing a variety of different activities, when they're mobile, and where these activities are being undertaken. The energy consumption implications of the activity travel patterns are calibrated based on the META dataset, which explicitly captures information from a sample of households about their activity patterns, travel patterns, other household characteristics, and energy consumption. So it actually provides the link between all the factors that we're modeling. And on the next slide, I'm summarizing the scenarios we simulated with our agent-based model. We have a combination of work from home scenarios and EV adoption scenarios, where the work from home scenarios are basically all workers working from home, or only non-critical workers working from home, or only 50% of non-critical workers working from home. Of course, we could look at a wider range of scenarios. In this instance, we limited ourselves to these. And EV adoption was a baseline of 6%, which is how things were pre-COVID, and then 30% randomly across the population, assuming that there's an increase in EVs adopted, but it's sort of randomly distributed across the population. Income-driven increase in EV adoption that ranges from 1% to 50%, averaging at 30% across the population. And the fourth scenario where 30% of the critical worker households are basically adopting EVs, since they do have to travel. And so the idea is to see how the synergies between working from home or not being able to work from home with EVs work. And a combination of these scenarios is what we present in the table 3 in the report, which you can look at. Finally, to summarize the results, there's a lot more detail in the paper, in the briefing papers. I won't go through all of it, but to summarize the key results, it's clear from all the results that the magnitude of EV uptake and residential electricity load is significantly, several percentage points, several tens of percentage points significantly higher than work from home policies. And also that the pattern of EV ownership in terms of how many EVs, but also who owns the EVs matters. The work from home effects on residential energy load will also vary spatially, depending on the socioeconomic profile of the area and the people who live there and the kind of jobs they participate in, the likelihood of owning electric vehicles and so on. It's also very clear that the work from home patterns play a role in driving the uncertainty, spatially as well as temporally, of electricity demand. And all of these leads us to conclude that a coordinated approach to EV adoption teleworking policies can be helpful, probably will be helpful. But there's a lot more than just work from home patterns and EV adoption. So the ongoing work is to look at more complex patterns of mode choice behaviors, as well as other policies that might coexist alongside all of these. With that, I'll hand over to the next chapter.
Thank you, Aruna. So, hi everyone, I'm Luis Badesa, and I'm a research associate at the Department of Electrical Engineering. And together with Professor Goran Starvaj, we have analyzed the challenge of balancing the GB grid during the 2020 lockdown. So I'll briefly introduce today what we found out. So first of all, why was there an operational challenge? Well, to understand it, we need to consider 3 main factors of the lockdown period. First, the depressed electricity demand. Second, that there was a typical power output from renewables in spite of low electricity prices. And this is because most renewables output as much power as possible, regardless of the price that they are paid for it, as they have 0 fuel costs. And the third factor was that there was a typical power output from nuclear plants, because these plants are also not significantly affected by market prices due to their inflexibility and low short-run marginal cost. So the consequence of these 3 factors was that we had 2 major sources of power during lockdown, which were renewables and nuclear. But operating the GB grid with just nuclear and renewables is not yet possible, because system stability would have been compromised due to low inertia. I'll explain a little bit what inertia means, but for now, just keep in mind that it helps keep the system in balance. But actually, we can extract very interesting learnings from this period on how to operate low carbon grids, because these conditions were not expected until 5 or more years in the future. So given that challenge, what did the energy system operator do to address it? Well, National Grid had to take a series of balancing actions with a total cost of around £300 million from May to July 2020. The main actions taken were first to create a new product called Optional Downward Flexibility Management, with the goal of procuring downward flexibility. So this service gave National Grid the option to either increase demand or curtail distributed generation, such as embedded wind and solar. Then the second action was to sign a bilateral contract with the largest nuclear power station. This largest plant defines the volume of ancillary services that we need. This practice is called the N-1 reliability standard, and it's widely used across the world. It means that if we have enough resources to cover for the largest possible loss of generation, we will also keep system stability for any other smaller loss. Then through this contract, National Grid could instruct the power plant to halve its output, effectively reducing the size of the largest possible power loss. And finally, the third type of action was committing gas-fired power plants to increase inertia. So these were plants that hadn't been successful in the wholesale energy market, which means that they were not needed for producing energy, but they were committed through the balancing mechanism simply for providing the needed inertia. Next slide, please. So as I said, the operational challenge was largely due to low inertia, but what does this inertia mean? Well, synchronous generators have a rotating mass, like the one you see in the picture on the right, and this is the inertia. And it's valuable because it stores kinetic energy as it rotates to produce the power that we consume. So in simple terms, inertia is a very valuable energy buffer that naturally helps stabilize the grid. And our modeling projects that there will be a radical decrease in inertia in the GB grid in coming years. This lower inertia will come from replacing synchronous generators like coal and gas plants by non-synchronous renewables like wind turbines and solar PV panels. Renewables lack this inertia, particularly a solar PV panel, which has no rotating mass at all, as you can see in the picture. So it becomes much more difficult to balance the grid on a second-by-second basis. So the key here is that inertia used to be a byproduct of energy because it was naturally provided by synchronous generators when producing energy, as you can see in the yellow distribution for system inertia in 2016. But it is becoming an insurance because we will have to pay for it independent of energy, and we need it to absorb faults that might happen in the system so that we can avoid imbalances. Next slide, please. And finally, as key takeaways from this period, I would highlight that the GB electricity grid experienced an operational challenge due to low inertia, that the cost of ancillary services during lockdown was around 3 times higher than in the same period in 2019, with a total slightly above £300 million, and that our modeling demonstrates that the cost of ancillary services could increase by an order of magnitude by 2030. But also some interesting learnings that we can take are that fast frequency response shows to be very beneficial in the future system to counteract this low inertia. And also that a stronger link between inertia and frequency response requirements will be quite important. That's it from me.
Thanks, Luis. So just to sum up the main conclusions and recommendations from the finding of the paper. So the rise of teleworking. So in this presentation, we've actually examined quite a lot of the influence that COVID has had on the energy system, and the conditions faced under lockdown allowed for a really unique glimpse of our energy system in the future and provided lessons on how we can prepare for a future of decarbonisation. The following conclusions have been reached, and here are the recommendations. So teleworking was a very big trend throughout 2020, with containment and closure policies forcing workplaces to adjust to a new normal. Whilst not the only consequences felt by employees and employers over the course of lockdown, teleworking is the only outcome that has merit in long-term applicability. Our findings suggest that on average, teleworking had an influence on reducing national electricity consumption, with workplace closures leaving offices absent of employees. And at a household level, a day spent teleworking increased weekly electricity consumption by 6%, but thanks to a highly renewable grid and a lack of commute, it didn't translate into an increase of carbon emissions. So part-time teleworking proved to be a relatively popular scheme in our survey and may be an avenue for businesses to explore to reduce their emissions. However, there are external factors that need to be considering before implementing a long-term strategy, such as the social implications of it, and it may not suit everyone. So the second conclusion, so this comes with coordinating policy approaches. So the influence workplace closure had on electricity demand prompted further investigation into how teleworking may influence our future household demand. In the activity-based model applied for the purpose of this paper, how two expected drivers of energy in the future, such as electric vehicles and working from home, interact was analysed. So the interactions between the impacts of these two factors are important to consider when designing appropriate policies to limit emissions. For example, the patterns of teleworking could be coordinated at employer or even city level with suitable incentives in the form of discounted EV charging at employers' premises during certain days. A systems-based approach is also very important to consider. So lockdown had a high level of renewable penetration, and this meant that there was an increase in household electricity use, but it didn't equate to an increase in emissions. When isolating for the greener grids of 2020, it was found that behavioural shifts in the time of use were not as influential in limiting emissions. So this reveals the need for a systems-based approach to reduce emissions, and to lean solely on demand flexibility is unlikely to be as successful. So with regards to managing the grid, the remedial steps taken by National Grid were successful in lockdown in that they prevented any major outages. In a future destined for high renewable penetration, however, it is important to act proactively. There's increasing levels of enhanced frequency response could provide the most cost-effective way to manage a low inertia system. As renewable penetration is also only likely to increase, it's important to recognise the opportunity that Great Britain might have in pioneering mechanisms relating to ancillary services. And finally, market conditions. As Luis said, there's currently no market for inertia, and it's notably relevant to understand how to make the current financial support systems in place allow for the provision of inertia and frequency response. This has potential to create market conditions more relevant for high renewable penetration and avoid the reimbursement for stopping the output of renewables. Thank you very much. I'll now pass you back to Tim to introduce the external panelists.
Thank you, Amy and Mirabelle and Aruna and Luis, for a clear exposition of the paper. It's my pleasure now to introduce three panelists who were kind enough to agree to preview the paper and gather some thoughts. So with us today we have David Sykes. He's head of data science at Octopus Energy. Octopus Energy, as you may know, is a technology business that supplies green energy to 2.7 million households and businesses. Octopus also licenses its Kraken platform to retail businesses internationally, and it's David and his team that build and maintain the cloud-based data engineering, analytics and machine learning capabilities that sit at the heart of that Kraken platform, and they do the forecasting of consumer behaviour and helping to optimise the hedging, pricing and operation strategies. With us also is Dr. Tina Fawcett. She's acting leader of the energy programme at the Environmental Change Institute at the University of Oxford. She's also co-director of CREDS, which is the Centre for Research into Energy Demand Solutions, and it's a multi-university research partnership. Her own research focuses on how and why we use energy as individuals and as organisations, and she explores pathways and policies to reduce energy demand and carbon emissions. Julian Leslie is head of networks and is chief engineer at National Grid Electricity System Operator. He's a chartered engineer with nearly 30 years of experience of transmission system operation, planning and investment. Julian is responsible for the transition of the system to a low carbon future and for defining the needs of the network so that the market and network owners invest in appropriate technology solutions at the right time. So, three people fantastically well qualified to respond to this paper. I'm going to ask them each to give their remarks in the order I introduced them, so I will turn to David first.
can you hear me?
We can now.
Brilliant. Sorry. So thank you very much for the intro. And I just wanted to firstly congratulate you all on an amazing sort of collection of research. I sort of saw firsthand the volume of work that just went into the data collection for just one segment of this. And so what we're seeing here is a very well put together sort of tip of an iceberg of a mountain of research that sits underneath it. So congratulations to you all for putting that together. There are sort of three things I wanted to talk a little bit about and draw upon from your findings. So firstly, I am very excited to see the household focus in many of the sort of parts of this research. I think for a very long time, both academia and industry have thought about domestic load as this sort of homogeneous block, maybe with a bit of temperature sensitivity, maybe with a bit of regional variation, but ultimately not really thinking about what drives that, which is consumer behavior right at the bottom of that. And so it's great to see like smart meter data, you know, which as an industry we spend a lot of time and money getting in place, and survey data, really understanding consumers being put together. And I think, you know, as we move to a world of half-hourly settlement, that will start to translate into commercials, and hopefully we can translate that back up into sort of system benefits if we have the sort of right market constructs, etc. So secondly, I wanted to sort of draw upon Aruna's great agent-based work. Again, brilliant to see agent-based models being used, starting to think about like consumer decisions and actually modeling individual consumers, because everybody is different and everybody has a different lifestyle, and so starting to push that through into scenario-based analysis is fantastic. What I wanted to sort of having read the paper, what I wanted to guard against is the idea, you know, it's lovely to see the idea of sort of coordinating transport policy, energy system policy, and workplace policy. I think we've got to be careful that we don't start. I think Luis showed like just how physical this system is, and Julian will know, you know, ultimately all this stuff sits on top of a very complicated, one of the most complicated machines we have in the UK, which is the electricity transmission and distribution system. And if we overlay sort of what I call incentive overlay, where we sort of overlay sort of quite crude price signals or incentive schemes on top of what is the physical system, we end up actually creating sort of perverse pricing incentives. And as an industry, we're trying to undo a lot of those at the moment, and put in place like really dynamic physics-based price signals. For us, that's the key to unlocking the right behaviors in the right places at the right times in a dynamic way. And then I guess the third thing was to pick up on Luis's analysis on the system level stuff. So I guess the irony for us is that over the summer you analysed, there was extremely low demand and an abnormally high level of renewables on the system. In September, so last month, there was abnormally high demand and abnormally low amounts of wind on the system, which, you know, has been challenging for us as a retailer. But that's a new norm that we have to get used to. What we're really keen to understand, and we work very closely with National Grid on, is how do we make sure that 70 million contract, rather than going into the pocket of the big nuclear generator, can start to be funneled back to the consumer. So how do we pay, you know, ultimately that 70 million has come out of the consumer's bill in the BSUS charge, which is embedded in the bill. That's the consumer's money. How do we make sure that they actually get paid if they're doing the right thing at the right time? So we got frustrated during that period and over the May bank holiday, because we couldn't participate in ODFM as consumers. We actually ran an experiment where we asked 35,000 consumers to turn up their energy demand. So do demand turn up rather than renewable curtailment turn down. We actually got 35 megawatts of turn up from 35,000 customers, which shows the sort of huge potential for domestic load shifting to rebalance the system ahead of time. So it would be great to sort of think about like what is the right policy frameworks, what are the right market frameworks, and what's the right operating model to be able to enable that. So that was all I had to say. So again, congratulations on a great study and looking forward to the questions.
Thank you very much, David. Let me turn to Tina.
Oh, right. Hello, everybody. Yes, I mean, I would like to add my congratulations to David. It's, you know, it's a lovely piece of work with lots of different elements that are all building up to something bigger, and that's really interesting to see. And I'm just going to reflect briefly on where it fits with the other things that are happening. You know, reflect on it as a piece of research, really. So obviously, other research groups and collaborations around the country are also trying to make the most of understanding what happened during lockdowns and this time. So, for example, UKIRC, the UK Energy Research Centre, and CREDS are working together doing quite detailed stuff on transport planning, which I think will probably fit very nicely with the sort of household surveys that you did. So different, you know, there's obviously a lot of research going on, and what you're doing is a really important part of that, and hopefully together we can build it all up to a really sophisticated understanding of what it tells us. I was really struck by a remark that was made at the start of the report, which I think has been repeated in the presentations, about how it's given us this unique glimpse into the future. And I think in the start of the report, you were really talking about the aspect that Luis was talking about the system. But actually, I think you've taken that forward to, you know, to also look at the teleworking and also look at the options for EVs, and trying to think about EVs and, you know, and linking those with the idea of key workers and different sorts of people adopting EVs is really interesting way of using this opportunity and your methods to look at the future. So I think that's, you know, that's really important, because we don't just want to analyze the past perfectly. That's, you know, that's not why you're doing this. Obviously, it's about getting this bigger understanding of our opportunities for the future. And you know, I mean, one of the real strengths of this work is the combination of evidence and methods that you've used. So to have this sort of octopus energy or the smart meter data, you know, to have also a whole set of questionnaires from people about preferences and views for the future, and then also to do the agent-based modelling and other things. It's sort of, you know, it's just this great combination of things, really, which is, you know, makes it very strong. And I think, you know, just to talk briefly about the working from home, I think, again, I think you would probably recognise yourselves, there's not going to be a definitive answer on this. I mean, people have been talking for decades, analysing for decades about, is working from home better for the environment or not, or better for energy or not? And as you say in your report, the answer you get depends on context, and it depends on system boundaries and rebound or changing behaviours. And so it's sort of, it's not that there can be a final answer, but it's, you know, what you're bringing to the debate is evidence. Because if we read the newspapers at the moment, there's endless opinion pieces about what's the future of work, are people going to be work flexibly, you know, it goes on and on, nobody knows really. But what you've done is you've brought evidence and modelling and these questionnaires asking people what do they think, and that's a really important part of how we move forward on this. So I think that's really good. I won't speak for too much longer. I'll just say I think it's really interesting. I'm really interested to see where you're going to take the work next. Thanks very much.
Thank you, Tina. And indeed, there are several other research groups around the country looking at various aspects. So I'm sure we'd be happy to collaborate and do the joining up. But let me move on now and ask Julian for his remarks.
Yeah, thanks, Tim, and thanks to the team. And like everyone else said, it's a great piece of work, and it's a level of detail that normally in this system operator we don't get to see, that individual household sort of behaviour. And obviously we're trying to manage 30 million households and trying to predict how that behaviour is going to happen and how it's going to change. And that was a real challenge in the early part of the pandemic, that we went into a lockdown with probably 12 hours notice, and that was it. And we had to work out what the demand was going to be, and then live through that and just learn on the job, as it were, and to see how things were behaving. So it's great now to reflect back and to get that very detailed analysis that you've been able to pull out from the data from Octopus or whatever, because that will absolutely inform us as we look to 2030 and 2035, when the electricity system needs to be zero carbon by 2035, how that's going to change the behaviour in the homes and how EVs fit into that, and how therefore we design a network and the tools and services we need in order to operate the grid. So the detail that's in the report is definitely going to feed into how we think about how we forecast that future demand and the role of consumers in that. I think that you're absolutely right. The other aspects, I mean, Luis is more the area which I'm focused on, but absolutely, we did get a glimpse of what the network is going to be like in 2025 and beyond. which was a bit of a shock because we thought we'd have three or four more years to sort of plan for that. But what it did enable us to do, though, was to really calibrate our tools and our models. So we'd never seen the network down at sort of 12.8 gigawatts, whatever. And we made lots of assumptions about demand and contribution to inertia and a whole bunch of other things. So as your report pulls out, it has allowed us to calibrate those models to really build us that confidence that as we move to 2025, when we have this ambition in the system operator to operate at zero carbon, that actually we are doing the right things. And the other aspects you pull out around frequency response and new markets for inertia, we are absolutely doing those things. So the Pathfinder projects are bringing in new markets, it's buying new technologies and new services. And in October last year, we introduced dynamic containment, which produces a frequency response within a second, as you point out. But we're not happy with that. We're looking further to the future with the FCC, further projects looking to get frequency response within half a second to really address this inertia and fast frequency response. And then one of your other recommendations was to look at Rockoff. Well, today is a historic day in our control room because we are no longer protecting for a rate of change of frequency at 0.125 hertz per second. We move to 1 hertz per second. So if we get a largest loss on the system today, we will have a very, very fast fall in frequency. But because of the dynamic containment, because of the understanding of inertia on the system, we feel confident that we can operate the network in that way. So a lot of the recommendations in the paper is either work we've got in train already, or actually we've delivered on some of them, and it is making a huge difference as to how we think and operate the network in this low carbon future state that we find ourselves in. So it's a great paper, it hits to all the points that we're managing. It will actually, as I say, inform some of our future work and help us provide better accurate data as to how we think about households and household demand.
Well, thank you to the three panelists for their warm words, but also for the insights from three very interesting perspectives on the energy system and consumer behaviour and demand. So we will move to the question and answer session. So thank you for those of you who have put questions in already. As I said, by liking the questions, they'll come to the top of the pile that I see in front of me, and I'm going to take questions in that order. And Guy Nicholson gets the prize for the most popular question, at least in early showing. It's two parts, so I'm going to ask the first part quickly, I think, to Amy, which is, did the team look at household gas consumption during lockdown?
This is probably more suitable for Mirabelle, who conducted the research, but I'll pass it on to her.
So we only looked at gas consumption recently, so after the report was written, because it was even more important to get a very fine control for temperature, and it took us time to get the right temperature controls. And the effect on gas is non-significant, so that we're still exploring how that can be. There were signs. What changed in gas was when it was consumed. So the total impact was nearly zero, but there was more. The time of the day at which gas was consumed was different. So people consumed less in the morning and less in the evening, and more around lunchtime. So we've put forward a few hypotheses, but not really found a conclusive one. One was that people showered less, or only cooked once, rather than different meals for different parts of the family. But yeah, nothing yet conclusive.
Well, we'll invite you back, Mirabelle, when conclusions have firmed up a little. So the second part of the question flows from that, which was to ask about whether the impact of heat pump energy demand would be more significant than EVs within the electricity demand, and that different timing considerations for heat pumps and gas boilers would be interesting. And I'm not entirely sure who I'm going to turn to. So I don't know, David, do you see anything in your data and forward look on how heat pumps would change demand patterns? Or is that not something you've got visibility of?
You're muted, David.
Oh no. Can you hear me now?
Yes.
I've got a very sticky mute button. I might leave it off for the foreseeable. So yeah, I was saying I can have a crack at that. So we have a lot of customers on EVs who we monitor, and we have a growing book on heat pumps. Generally, heat pumps are designed to provide sort of a stable heating load across the day, whereas an EV you can see it as like a block. So an EV is a much more flexible, high power load than a heat pump, which might provide lower power. So in terms of how you might see the impact on the grid, I guess if EVs are like, we just roll them out and we don't provide smart charging and smart tariffs, we'd probably expect EVs to provide to land a sort of bigger instantaneous signal, perhaps at peak time when people get home and plug them in. We have a tariff where we encourage customers to plug them in at midnight, and we see a peak that's bigger than the evening peak, so that is a secondary peak. Heat pumps, the impact on the electricity system of heat pumps really depends on how much thermal storage we install with heat pumps. So are we installing heat pumps with hot water tanks? Are we installing heat pumps with, your home is a wonderful thermal store if it's insulated properly. So, and there's also some really fascinating new thermal batteries coming out. And the key is that, we have to work together as an industry to come up with the right price signals to ensure that those storage solutions are economic to put in. So, and that means like prices should be expensive at peak time when there's not much, when there's a sparsity of renewables on the grid, and cheaper when there's lots of renewables and the network capacity is sort of open. Hopefully that answers the question.
Thank you. Does anyone else from the panel want to come in on that? Perfectly fine if not, because I'll just go to the next question. I think I might do that. So the next question, this just shifted in front of me, was about time. Sorry, by sorting by order, if one votes up high and suddenly it moves in front of me, my apologies, I shouldn't do this perhaps. How does time of year during which lockdown happened impact what we might conclude? So the first lockdown was spring, early summer, and that might have had quite a big impact therefore around lighting use and so forth. And the later lockdown was in winter. Would that really have changed carbon impacts or other impacts? Mirabelle, I'm tempted to go to you first for that.
Thank you. It's a good question. So we're now turning ourselves to the second lockdown. It's a bit harder to do because the behavior change was more diverse. In the second lockdown, kids went to school. In the third lockdown, they didn't. So all of that we could try to control for. I mean, as I said, I think the change in behavior was notable for sure in terms of when people change. But what also, as I said, our conclusion was that just that changing in the timing is not sufficient to have a real carbon impact that we need, as David highlighted, price changes, more flexible prices, and people to have better incentives to change and flatten their consumption. Where there will also be changes in the types of electricity demand, appliances, EVs, heat pumps, etc. That would affect that. So my expectation isn't that the time of the year would have had major impact, but maybe again David might have ideas.
Or indeed anyone else who wants to follow up. David?
I think we already covered it pretty well. So yes, I guess obviously.
Oh, we lost audio again, I think.
Can you hear me?
Yeah.
Terrible for a technology business. So obviously heating load over winter is the big determinant, and also the availability of renewables at the right.
I'm going to just move on, David, while you overcome whatever difficulty you're facing. Julian, can I put a version of that to you? I don't think you were worrying very much about peak demand during that period, but are you thinking of the future in a system which is perhaps less peaky because of some of these behavioural changes?
I mean, what I'm hoping that is going to be the solution. I think if we add in all this EV demand and domestic heating demand onto the peak, then it's going to be a real challenge, and we'll be investing huge amounts in the network just for an hour a year type thing, which is just obviously not sensible. So I think that by, I don't know, at some point in the next 10 years, we'll switch from dispatching generation to meet demand to actually a position where we dispatch demand to meet the available generation and capacity on the network. Because it's the generation we can no longer control, but if we have EVs and batteries in people's homes and the ability to load shift people's domestic heating or whatever, then actually that combined with grid scale storage, which we're going to need as well, that those things together, I think, will fundamentally change how we think about balancing the system, and we'll balance the system with demand rather than balancing it with generation. So we need to make that transition at some point. How we get there, and we're sort of in a halfway house now. There's over a gigawatt of batteries that are within sort of the balancing mechanism today, and they obviously start to play that role where they are sort of charging at time of high renewable penetration because the price is low. And as David said, the Octopus trial that they did had consumers participating in that as well, which is a great advancement from the Economy 7, which we had back in the early 80s, which was to keep the nuclears sort of fully loaded overnight. The Economy 7, we still get a peak at 1 o'clock in the morning today. What we need to be careful of, though, as David said, what we can't have is all of the EVs and heat pumps all using the same signal, all at the same second, all at the same time, because that will just create another operational challenge. So my theory is in the future, I'm going to be talking to Alexa and Google Voice and people like Octopus to say, look, can you just put a bit of a variable in there so it happens over 5 minutes or 10 minutes or whatever, depending on the size of the change. So actually the rest of the system can keep up with it. So it's a real fascinating space as we get more consumer and demand side intervention and interaction with the energy system, how we manage that to avoid creating another problem where it's all taking the same feed, either from price or carbon intensity, and all these devices start operating all at the same time.
Yeah. Tina, I'm going to bounce part of that across to you. So Julian's narrative included the lines about moving to a situation where demand follows available generation rather than generation following demand. That throws quite an onus on how energy supply companies interact with consumers. Are you confident or not confident that we might be able to affect a change of that nature?
Well, it's interesting, isn't it? I mean, I think speaking as a member of CREDS, I mean, we've just published a set of low energy demand scenarios which look at plausible, a route to reducing UK energy demand across all sectors, not just electricity, by 50% by 2050. So I think part of this story has got to be reducing demand, isn't it? Obviously, a heat pump in a well-insulated home is a lot less of a problem for anybody to manage and time than a heat pump in a not well-insulated home, or a system that people can't control to get the temperature they need and all that kind of thing. So I think we should think about demand reduction first. And then, yeah, I mean, there is quite a lot of work with, obviously a lot of people are looking at what will consumers wear in terms of flexibility and different sorts of consumers and different sorts of incentives. And often and obviously Octopus are doing that with their time of use pricing, and I've got colleagues who are on that, and obviously there some people that appeals to, and other people just don't necessarily want that sort of interaction. And there's a range of philosophies. I mean, I've been at energy conferences where sort of people running energy companies have gone, like, the last thing I want to think about is energy use, just make it all happen for me. Whereas other people have got a model of consumers as having to become much more engaged, becoming prosumers, getting very interested in the energy system. And probably what we learn from things like agent-based modelling and other approaches is actually, of course, we shouldn't be talking about one set of consumers and one set of answers. But it's a lot to learn,
Yes, indeed, a lot to learn, and that very good reminder that we shouldn't think of consumers as a homogeneous group. There are very many different types. And Aruna, that might be a point you want to come in on.
Yeah, I just wanted to briefly also add, going back to the original question of seasonal effects and heat pumps and so on. I actually did respond to Guy Nicholson's message directly in the chat as well. But the point I'm trying to make is the advantage of the kind of multivariate models we have embedded in the activity-based model system is that we actually have a seasonality variable in it. We also have the presence of gas boilers, and that data set we used, there were gas boilers, not many heat pumps. And so we could actually look at the impact of gas boilers on electricity consumption. And that is taken into account when we're actually running that model. And actually, as long as that kind of data was available, in fact, including heat pumps, we could actually predict some of these scenario analysis much more realistically to look at how things might vary into the future. And then coming back to behavior, prosumers versus consumers, I think there's got, as you rightly said, Tina, there's going to be a combination of both. And accordingly, I think the market's going to produce a combination of solutions, aggregators and smart methods to get either make it easy on the consumer or to get more interaction from the consumer. You set certain factors that drive your needs, or you just sit back and say, I just want my energy prices and my bill to be as low as possible, and I want these things to work well. Do what you will with the rest. There might be all combinations of these, and presumably the market will respond to that.
Thank you, Aruna. I think I'd like to draw Louis in and perhaps Julian to the question which asks, has there been an exploration of kinetic batteries that mimic the storage effect of inertia? So it's really about what are the technology solutions perhaps for creating more inertia in a system? And Louis first and then Julian.
Sure. So when we talk about inertia, it's true that we refer to this rotating mass, right? But in effect, we just refer to energy storage. It's kinetic energy that's stored in that mass. The really useful thing about synchronous inertia, so the rotating mass in thermal plants, is that it's electromechanically, so all the devices are coupled in the system. Therefore, it's just a spontaneous response. We can, however, define better controls to, for example, extract the kinetic energy that is there in a wind turbine. We can use devices like grid-scale batteries, but also smaller scale devices, probably, to provide these fast power injections. So the options available are many, actually. And I know that Julian and the colleagues at National Grid have been looking at synthetic inertia, also synchronous condensers, right, which are these rotating mass that would be there just for inertia, but not really, we wouldn't have to burn gas for that. So it's just a matter of trying to get the most cost-effective option, and there will not be a single answer. We'll probably use many of those, but getting to that right amount by probably creating tenders like National Grid is doing, so that investors finally choose the right products because they are the ones with the lowest cost. That's the way to go, in my view.
Thank you, Julian.
Yeah, and I think that we're now running 3 phases of a stability pathfinder, and in phase 1, 3 of those products have gone live, or 1 is about to go live, and that's everything from a standard sort of pumped hydro plant that spins in air and water, providing inertia, through to D-side, which was an old CCGT that had closed, which has now been repurposed and acts as a motor and rotating mass. So it's a very low-cost solution, reutilizing and repurposing an existing asset. And we also have, I know guys on the line here, but Guy Nicholson and Statkraft have been working with GE to create a new grid system stabilizer, which is just designed specifically to provide inertia on the system. It's still a rotating mass though, but it's designed to have a lot of weight and to provide a lot of inertia for its relative size. So having a market-led approach by defining our need and getting technology providers and innovators to come in with new solutions. As we look further forward though, what we are looking and really excited about is there's a Scottish Power renewable wind farm in Scotland called Dessalec, and that is using a grid-forming inverter and really smart power electronics to behave as though it is a rotating plant with inertia on it, so synthetic inertia. And I'm really excited about the results of that project, and there's a lot of work to do. It takes a lot of investment, but I think as we sort of get through that process and we crack the performance of these grid-forming inverters and those very fast power electronics, But actually that then opens up for storage devices and other renewable devices. It does open up a sort of inertia type market. It's whether it's inertia or really fast frequency response, and that's an internal debate we always have as to where you draw the line between inertia and frequency response, because the two are intrinsically linked.
Thank you. I'm going to take another shift in topic, and we're going to talk a bit about the nature of the sample of consumers we were able to look at. So the question is, there was a change in demand in the residential sector. You saw that it was perhaps subtle rather than dramatic. But off the back of that, what can we say about the sample size? Do you think you're getting a properly representative sample? So what was the size of the sample shared by Octopus, and how did that let you analyze the daily profiles and as they vary by the type of dwelling or type of household? So maybe Mirabelle and David in that order.
Thank you. So the households that accepted that we would look at their data was more than 1,100 households. So and we checked how representative they were from the regional data that Octopus shared with us, and they were representative. Also, while it might not seem a huge increase, 10%, we also first thought about that. But if you think of how much electricity you consume as a household, a lot of it happens regardless of whether you are in the home or not. So your fridge is running, your dishwashers are running, your laundry, etc. So the extra consumption from working and remote schooling would have been computer systems and maybe a bit more lights, etc. So I would say, in my view, they were representative. They were around the country, not located in a given place. I mean, David might add that Octopus customers are special.
David, do you want to pick up?
Yeah, I'm going to try. Can you hear me okay now?
Yes.
Thank God for that. Yes, I mean, just to clarify, they weren't taken from our smart tariff set. So these are, I don't like the concept of normal customers, but these were like fixed tariff customers taken from they had to have smart meters. So, there's an slightly inherent Octopus bias because they've chosen Octopus. There's a slightly inherent sampling bias because they've chosen to answer a survey, and there's a slightly inherent smart meter bias because they've got a smart meter. That said, we have close to 3 million customers now, so we're like a large chunk of the UK base. You can never prove if they're fully representative, and actually working out what representative really means in energy retail is quite hard, but I think they're a good sample of normal fixed tariff customers.
Thank you. And Aruna,
and if I can, sorry.
Yeah, go ahead.
I was just going to add that we did run the analysis looking at whether there was a differential effect based on property size or price of the property even, and that at least with our econometric approach, there was nothing noticeable there.
Okay, thank you. Aruna, your models could disaggregate some of that stuff, look at effects of property size or household size or whatever. Yeah. But please answer that, but also what data do you need actually to then calibrate your model sufficiently to do that?
Sure. I was actually going to say we do actually have some variables in our model that I think, if I remember right, were significant, which had to do with the type of property the household lives in. So ideally the kind of data we need is data about households ranging from the type of property, the properties of the building itself, the appliances they have, the activities of the individuals, and the energy consumption. So if we had data for all of these in the same household, or set of households rather, and if it's representative, we know that the models we calibrate from this data can be used reliably across a population. When it's not representative, we'd have to think about how representative the models and the parameters calibrated are, which is often the issue. Having said all this, there are methods, data science methods basically, where even if you don't have this data from a single household, if you had it from different households, or rather different samples, you could use data fusion, which accounts for the errors or noises that creep in from using different samples of data in calibrating such models. The only problem with such models is that unless you have really large data sets, the parameters we calibrate will not necessarily easily get to be statistically significant. There'll be a lot of noise around them, effectively. So yeah, that's it. I don't know if that answers your question.
Well, that was my additional question, and I shouldn't perhaps be answering them anyway. So let me go back to the list. Asked anonymously, someone asking us, how did we do the correction for weather in the domestic energy demand? And either Amy or Mirabelle, I think, perhaps first to pick up that. I know there was detrending of the temperature and being across sort of April-May period as the winter heating demand starts to reduce from the system, there was a detrending necessary. How was that done? Neither of you are unmuting, so.
So in our part of the briefing paper, we collected data on temperature disaggregated throughout the day at the postcode level. And so we then use that data in our econometric analysis to control for each household's temperature. And because our approach is to really compare the same household in the same home in 2019, say on the first Monday of April in 2019 versus the first Monday of April in 2020, controlling for any difference in temperature on those 2 days at a given hour, then we feel we're capturing any effect that temperature could have.
Thanks. And in the work that Ian Staffel did in the earlier chapter on national trends, I know that he had looked at previous data sets and temperature correlations and worked out correlation factors and detrended. So I'm going to refer the questioner to the report for the detail on that. Where am I going next? So Mike Wilkes has asked a question about the implications on distribution networks and DSO. We had a bit of a national scale ESO focus rather than DSO focus, but the changes in system characteristics and indeed demand will have affected that. Louis, are you able to comment on perhaps implications for DSO as well as ESO?
Well, one thing that comes to mind is that it will become much more the grid will become physically much more complex. If we bring in more of these inverters, which are devices that we need when we have renewables, but they have to somehow coexist with some synchronous machines, so some old assets, if you wish, which still have these rotating masses. Everything becomes much more complex, but much more interesting also from our side of the research. And one key aspect is that all these stability needs, the frequency services, etc., start to show a regional trend. So we have already seen that we won't be able to assume that the frequency and the electricity grid, which just means the magnitude we need to measure to understand if there's an imbalance, we will not be able to assume that it's equal throughout the grid. There will be some regional differences. For example, in the UK, where we have Scotland with much lower demand than the south, but a significant capacity of onshore wind. In the future, also probably some offshore wind farms might feed into the Scottish region. We have this regional aspect, and for that, well, we could still take a transmission level view and rely on grid scale assets, and that's certainly possible. But I think there's a huge opportunity opened by the electrification of transport, the electrification of heating, Therefore, the DSOs might play a really big role there. It's probably going to be really complicated. There will need to be some, well, very significant interactions between DSOs and the ESO, but we should be able to extract all that flexibility, because that can really lower the costs of operating the future system. And again, we will need to really focus on where we get this flexibility from, given that the regional aspect is going to become more important.
Thank you, Louis. I probably should have folded in the question from Andrew Roper from quite early on in the discussion, which also noted the local network impacts, you know, and the shift between office working and home working, and EV and heat pump use, changing where we think, over-interpreting, possibly changing where we think perhaps some of the local constraints might pop up. David, you said you wanted to come in on this, so I'll take you next, and then I'll follow up with Julian if he has any comments on this general issue. David?
Can you hear me?
Yeah.
Excellent. So yeah, we've done a lot of thinking on this, and we speak to a lot of the DSOs, or DNOs as they are now. I think the interesting thing about our energy system at the moment is that the ESO is responsible for managing frequency, stability and balancing across the whole energy system. And really the DNOs, one of the best description I heard from one of the DNOs a while ago is they're kind of infinite bus bars at the moment, in that they don't really have that much local constraint yet. So they're not having to actively manage their networks. You know, UKPN in London may be a bit more than others, but generally not having to do too much active management of their networks. We're going to move to a world where they have to do a lot of active management of their networks. And what that ends up with is two parties not competing, but both trying to manage power flows in the same bit of the energy system. So one of the key things I think we need to do, and I think, you know, the FSO consultation that's just gone through will play a bit of a role, and the ED2 stuff going through the DSOs, is define that interface and who's responsible for the management of different parts of the system, when otherwise we're going to end up with a sort of spaghetti junction of, you know, retailer, aggregator, DSO and ESO all trying to control and optimize for different things at different times in different parts of the system.
Well, that's a nice segue into Julian, who I know is concerned about the whole electricity system operation and the DSO-TSO interface. So Julian, what do you want to pick out of that?
Yeah, I mean, it's a fascinating subject, but we absolutely need to operate in a whole electricity system as a minimum. And we see a lot more of that even today. And as the DNOs become DSOs, that needs to increase even further, and commonality of everything from commonality of sort of market structures and contract arrangements, but then the technology that needs to allow the DNOs to sort of resolve a local streets issue or a local neighborhood issue. And then if we've got devices in there providing national services, then knowing what is left and what capacity is left. So as David says, we don't get up in this when relying on something that the DNO has already sort of taken out of service or whatever. So our whole coordination optimization is going to be huge. We need to do on a whole electricity system today, but as we move into the FSO piece, we need to do a whole energy system basis as well. And we need to be able to optimize and coordinate across all of these energy vectors and do that balancing in close to real time. So it's just going to become much more and more complex. But the DSOs, though, back to the question, the DSOs are fundamentally part of this. They've fundamentally got to understand how the consumer behavior is going to work on the streets with the electric vehicles, the batteries in the roof and the solar PV, so batteries in the loft and solar PV on the roof, and how all of that can be optimized, and how much the Internet of Things comes into the home. And when you press the button on your dishwasher, does it start straight away, or does it wait for a signal from something that then makes it come on later in the day, and optimize all of that? And that's managing the national basis and coordinating that with the sort of national sort of generation output, but also having to manage that local constraints in the local streets or the local neighborhood.
Thank you. I've seen some nice little technical questions about the risk of a higher rock-off limit and various things, which I'd love to discuss, but I fear it might be a bit narrow. So maybe Julian and Guy Nicholson could pick up on that in a side conversation. I would like to go back to perhaps the consumer interaction. There's a question from an anonymous source quite early on about time of use tariffs. So recognizing that they're great for adding flexibility into the system operation, That's the plus, but they increase uncertainty for individual consumers, especially given the current environment, as remarked there, and the uncertainty over prices in general and time of use prices and increased spikiness. So what are the implications of that? How do we make it easier for households to adopt time of use tariffs without perhaps having the burden of uncertainty? Or the, several people can comment on that. I think I would quite like to ask Tina if she has a view on that, and then I might go to David and Mirabelle.
Well, I mean, yeah, I don't have the answer, but I would say I'm involved in there's 3 big Innovate UK demonstration projects at the moment that are sort of looking at issues of storage, electric heat, electric vehicles, and integrating different bits of the system. And 2 of them are in Oxford and Oxfordshire. And the one I'm involved is called Energy Superhub Oxford. And one of the things that's happening there is that ground source heat pumps have gone into social housing. And one of the benefits will be if they're run with a sort of variable price tariff, could be, but you know, that's the tenant's choice, and there's a downside to them of adopting variable pricing, and they're people on low income. So is it actually ethical to, they can't be required to do that. Should we be persuading them to do that? So this is a real issue we're facing in research at the moment. You know, what's, you know, and we know we're in a particular moment, you know, a particularly difficult moment right now with energy prices, of course. But so I think, yeah, I mean, there's, you know, there's a lot to understand about this, but I'll leave it to others who may have some more answers than questions.
David, this must be something that plays on Octopus's collective mind.
Yeah, so I think the most important thing is to distinguish between time of use signals and time of use tariffs, and the 2 don't have to be linked. So the system runs on time of use signals at the moment. They're quite weak and they're not locational. But you know, we carry the risk of wholesale pricing for our consumers throughout the day. It's different at peak time to off-peak time, and it's our choice in combination with consumers as to how we package that up. And we win as a retailer by building the best package for consumers. So that package for some consumers might be a fixed time of use, so it's fixed at different times of day, but you know, the rate is the same all the way through the year. At night time, we have tariffs like that. It might be a variable time of use for your more engaged consumer. Crucially, you know, I think the industry has really conflated time of use signals and time of use tariffs, sees things like, you know, the ERCOT gritty time of use tariff debacle and goes, time of use tariffs can't work, that means time of use signals can't work. Let's make sure we get the right signals which reflect the physics of the system in the right place at the right time, and then give retailers, like unbound retailers, to be able to provide the right tariff constructs to deliver that. And what I mean by that is, you know, Ofgem do a great job of regulating the system, but like they're quite prescriptive about what we can put on bills. And actually, a lot of our time of use tariffs, which have been very successful and very popular, we've slightly not broken the rules, but slightly like gone outside with their permission of the existing regulation. And the key is, like, you know, no one tells Tesco what you know, what promotion they should be doing when, or at what time of year, and how they should write, and what they should write to customers about that. They have a Weights and Measures app which tells them how to do that, but they're then free to come up with the right sort of construct, commercial construct, and consumer proposition.
Thank you, David. We're a little bit tight on time now. If Aruna or Mirabelle want to make a point on this issue, you're welcome to, but don't feel obliged to. You okay? Okay, that's kind of you. Thank you. Thank you to the audience for being engaged and asking such an interesting and varied set of questions. Thank you very much to our 3 panelists who not only pre-read the report and came up with the remarks, but then allowed me to throw questions at you at a variety of different topics that arose during the conversation. So thank you very much for helping us out today and being great at it. And thank you for the 4 authors who presented today, and standing behind them are several co-authors who contributed to the report. So thanks to everybody who made this a stimulating and interesting debate. I encourage you to go and download the copy of the full report if you haven't already done that while we've been talking, and you'll find a great deal more detail in there that I hope will stimulate further thinking in your own minds. So with that said, have a good afternoon. I look forward to seeing you at a future event.